It's a great pleasure for me to introduce Rodrigo to the Institute. Rodrigo is, well, I know Rodrigo since we met at the UCSD, University of California, San Diego. He's a very bright and young theoretical physicist who has worked on many different topics, spanning from high energy physics phenomenology, flavor physics, Higgs physics, and one characteristic of his work is that he tends to, and he tries to address very deep questions and connections in theoretical physics. For example, recently he has been working on connections between axion physics and wormholes, bottom-up quantization of gravity, renormalization and quantum corrections to gravitational interactions. And more recently, he has been working on this project that he's going to talk about today, related to the baryon asymmetry in the universe and its relation to the really dark matter that we observe astrophysically and cosmologically. So let me just finish with a very brief overview about his career. He graduated from the Institute for Theoretical Physics in Madrid in 2013 under the supervision of Belén Gabela. He worked then as a postdoc in UCSD, where I met him for the first time, and then at CERN, and finally at the IPMU in Tokyo. And since the end of 2019, he's faculty at the University of Durham, where he's currently an assistant professor. So without further ado, I would like to give the floor to Rodrigo so he can tell us about this beautiful project he has been working on recently.
Before Rodrigo starts, I just briefly remind the audience that the questions will take place via the chat, the Zoom chat, or they can also post questions in the chat of the YouTube channel, which will be checked. And also they could also send questions to the seminar commission, the seminar commission email address. Okay, but you know, even if I mute the attendance during the meeting, people can still ask questions, use the chat to ask a question, and then I will try to stop the speaker so that some interaction can take place. Okay.
Also, let me, in connection to this, let me also mention that Rodrigo is with us until May 20th. So if you want to discuss with him or have any questions beyond what is going to be discussed here in the seminar, you can meet him at the office number 1506, or you can send him an email or whatever. Okay, go ahead, Rodrigo. The floor is yours.
Thanks very much for this introduction. That was a very nice one. I hope I live up to the hype now with this talk. I leave it up to you if there's questions that are best addressed during the seminar. I don't mind stopping and explaining any given point. Because for this talk, I've tried and adapt my latest research to the audience, which means that this is going to be somewhere in between a review, a research talk, and a lecture. So please, if there's anything that you're not also familiar with, you can always stop me for questions or ask later. And there's another point that you might have noticed already. This is a handwritten talk. Let me apologize for that if anyone finds this unpleasant, but I've done it a few times and nobody complained so far. So up until you complain, I'll keep doing it. Here's the outline of the talk. It's rather simple in its organization. I come, as Jorge pointed out, from a particle physics background, but there is this, as you know, rich connection with space, looking out into space, and fundamental physics are deeply interconnected, and in particular, the experimental data flow from looking out into space for particle physics and for fundamental physics is a very fruitful one. And I'll go over a few of these experimental evidence to later focus and narrow down into two topics, which are that of dark matter and baryon asymmetry. And as opposed to this first part of the talk here, I'll be more speculative, talking about the proposed solutions to these puzzles or the new physics that might be behind the evidence. And then in the last part of the talk, I'll talk about my own contribution to this in my recent work with, I should say, collaboration with Jacob Scott, who's now in Torino, I think, but he used to be at Durham. So let's get it rolling. What can we learn about fundamental physics looking out into space? I'll talk about 3 points. In particular, dark matter, dark energy, and the baryon asymmetry of the universe. There's others actually, but we just don't have time for all of them. It's also inflation, but I'll only mention it on passing. And as I said, this first part is only for hard evidence, and I should, in that sense, already qualify this first slide. So I'm calling this evidence for dark matter, but some other people would say this is evidence for modifying Newtonian dynamics. I particularly think this is evidence for dark matter, not because of this only, this data only, but the fact that the picture of a cold substance, the picture of dark matter, fits other observational data like structure formation. So having said that, there's since quite a few decades ago evidence that, for example, the stars rotating in galaxies do so much more faster than one would deduce from counting the luminous matter that is in the galaxies. So you would expect that these rotational velocities will fall with distance once all of the luminous matter is contained within it, within the radius. It doesn't happen. It's actually pretty stable, which points towards some extra matter in there. We won't be modifying gravity in that sense. And just as well, we look at galaxies, which are bound gravitationally. And again, counting stars, or the luminous matter, also dust, I should say, we find that that matter doesn't produce a gravitational field strong enough to have the system bounded. So we suspect there's something else at play in there. And there's also evidence from gravitational lensing of light, or here picture is the bullet cluster, where we see two galaxies go through each other with the bulk of the galaxy passing through without interacting. But I presume this audience knows more about this than I do, so let me not embarrass myself any further discussing this in front of you. Let me tell you that the consequence of this for us particle physicists is that our pride and glory, that is the standard model that we can summarize in this table of elementary particles with a number of quarks, leptons, and the mediators of our forces, including, if you want to throw in there gravity also, there's the graviton, there's electromagnetism, the weak interactions, and the strong interactions, and the Higgs as it pertains electroweak interactions. Well, none of these matter can account for this missing mass in these systems, so we have to add up a new substance, a new particle, or more than one, at least one, to make up for this extra matter in the universe. And there's no shortage of candidates in particle physics. You know, the field, we've always proposing new theories, and there's always new particles to play the role of dark matter. If we take our scale and we zoom out even further to the hundreds of megaparsec scale, we can, for example, map the universe with galaxy surveys, as in this graph right here. And if I didn't tell you what this was, you were just looking at it without knowing that this were the position of galaxies, you will think, well, this is a substance. And what I can observe is that if I go to any point in here and draw a circle big enough, that point will look like any other point in this substance. So it's pretty homogeneous when you go to large enough scales, and also isotropic. That's an observation that's further supported by looking out as far as it goes with light, as far as we can see. The first evidence for this physics was detected with this horn antenna that you may be familiar with. But when you have that big corporation as the Bell Corporation lent their apparatus to a couple of physicists, great things can happen, namely the discovery of the CMB. And to describe this homogeneous and isotropic universe, we can start from, there won't be much math in here, but here and there we'll have some equations. The Hubble law that is telling us that the velocity of a given galaxy that we label with this index I is proportional to a constant and the distance of this galaxy. And this is a linear correlation that you can see in this original plot. Perhaps it's not so convincingly following a straight line, but as you know, there's further data that tells us that this is really the way it is. And we can choose two parameterized distances and explicitly separate the time dependence in this distance into a space-like coordinate that doesn't depend on time, and a scale factor, A of t, that does depend on time, and so the velocity will be the time derivative of that. And if we do this, we have that xi drops out, because it doesn't depend on, because this law doesn't depend on the galaxy in particular you're looking at, it's universal. We get this expression for the Hubble rate as the time derivative of the scale factor over the scale factor itself. And is a property of a universal property in that sense. Like I said, it doesn't depend on galaxies. And in the sense, it's telling us about space-time itself, which we can further expand on if we write the invariant line element and introduce a metric. Again, this is the way we choose to describe the physics. So there's a big ambiguity in this, but this is the standard. And we have, again, this comoving coordinate that labels galaxies if you want. And in particular, we have that this, for a given galaxy, this label stays the same. So for example, we have here a galaxy at 1 megaparsec, and even in the future, the comoving coordinate will still be 1 megaparsec. But the physical distance will change with time, and the physical distance is the scale factor times the comoving distance. And just for normalization, we choose this comoving distance to coincide with distances today, with T0 means the time today. Again, this is a way to describe the system. That's how we do it. But what is relevant is that given our description of the system, we can use Einstein equations to study the dynamics of a system. So out of that line element, we can write a metric that looks diagonal, and in particular with the scale factor squaring the space-like components. To be consistent with our homogeneous and isotropic ansatz, we have a stress energy tensor that contains in its first component the energy density, that's energy per unit volume of whatever substance we're describing, and then the pressure term for the space-like component. And this metric plugged into Einstein's equations returns Friedman equations. There's two of them. One of them is honest evolution equation with the derivative of Hubble that contains therefore two derivatives of the scale factor. But the other one is a constraint equation or a budget equation that telling us that the square of Hubble equals Newton's constant with a prefactor times the sum of the energy density of all substances in the universe, because gravity is universal in its couplings and it couples to every type of matter. And we can even throw in for fun a cosmological constant in there. As it turns out, it's not for fun, it's for real. But we can connect this budget equation with the actual budget of substances in the universe that, as you know, have been measurable via different means, but one of them is the CMB. And we see that actually what we know as ordinary matter, which is basically baryons, as we'll see, it makes up a mere 5% of the total energy density in the universe. Dark matter that we've already introduced makes up 27%, with the rest of it being this mysterious dark energy substance. And just briefly, a bit on the type of substances that we have in there. We just said that matter makes up a sizable portion of this contribution to the energy density, and we call matter anything that is non-relativistic, basically, whose energy is given by its mass, rest mass. So it's moving slowly in that sense, it's non-relativistic. And then energy density simply scales with 3 inverse powers of the scale factor because of this dilution of volume. In opposition, radiation has that its energy is given by its frequency, or the inverse of its wavelength, and there's an extra factor of the scale factor because this wavelength is being stretched out with the expansion. We could even stretch our definition of substances to also include curvature. It could be in a higher dimensional sphere or a hyper surface. As it turns out, experimental evidence tells us that this term is very small or missing in our universe. So we live in a very nearly flat universe. And the other type of substance is if there's nothing like the above, and there's simply energy density associated to empty space, to vacuum, then we'll have just a constant contribution that doesn't dilute with the scale factor. And that, if present, it will eventually overtake the other contributions that will necessarily dilute with the expansion. And while this is, in a sense, simple to implement in our models of particle physics, and in a sense, the leading order term in the expansion, I'll elaborate on this a bit further, but basically what I mean by expansion is we describe our physics via an action that is the interval of a Lagrangian, and we count the dimensions of our terms, and in that sense, the constant is the simplest term that you can write in there, followed by terms like the Higgs mass, for example, in the standard model, or the Ricci curvature, it depends on space-time. And while this term is easy to add in our expansion, when we take this, the full theory to be quantum, we're at a loss of the actual value that we measure experimentally, because we expect naive contributions to this term interaction from quantum processes to be many, I'm talking maybe 100 orders of magnitude above what we measure. So, and this is a puzzle that really, really puzzles us a lot. There's not much we know about this. That's something, another input into high energy physics from looking out into space. And then for the third one, we look at the CMB a little closer now. If you look at the intensity of the photons in the CMB, as plotted here from the COVID satellite, you see, or you barely see, but blue is the fit and red are the points. The distribution follows exquisitely close a black body radiation spectrum. But a black body radiation is the signal of thermal equilibrium. And when we look out into space, we see galaxies and voids, but nothing like equilibrium. So how could it be that we were in equilibrium, at least far enough in the past? Well, this is to understand that if we rewind back the tape of the universe, if things are expanding now, they used to be much closer, with the potential of cramming together a lot of matter and interactions between it. And we have that thermal equilibrium could be maintained if the expansion of the universe was in some sense smaller than the interaction of these particles in the primordial plasma. We can put actual equations into this. The interactions in the plasma will be proportional to the cross-section for a given process, something that we can compute from first principles, times the relative velocity, and then n, which is the number of particles per volume, or the number density. This has units of flux, and this has units of area, so this is the interaction rate. Provided it's much larger than the Hubble rate, we can approximate a system to be in equilibrium and use the adiabatic approximation. And then after computing our magnitudes as if we were in a static system, then introduce a time dependence for the expansion. And we can recycle Friedmann's equation into the square of Hubble, being again the proportionality of the Newton constant. But a contribution from, and we're talking now the early universe, from radiation, you can compute the energy density in radiation in a black body distribution, and you get that is proportional to 4 powers of the temperature. And there's a prefactor here that counts the number of relativistic particles. And now early on, there's many more relativistic particles because the temperature used to be much higher. And a relativistic particle is one whose mass is much smaller than the temperature. And there is also a contribution here for matter, written here in somewhat atypical notation. But basically, we can write this as proportional to 3 powers of the temperature that contains all the time dependence, and in particular, to make it consistent with the previous discussion, the temperature decreases with the scale factor, inversely proportional. And 2 main contributions that we've already seen in that pie chart in the form of dark matter and baryons, which, well, here we're splitting, like we said, the energy is dominated by the rest mass, and this factor y, that is the yield, is related to the number density, as we'll define more precisely in a minute. But what we do know from that pie chart is that the product of these 2 terms compared with the product of these 2 terms is roughly, so this is roughly 5 times larger than this, coming out of that pie chart. Let's look a bit closer at this yield y for baryons. About the notation, I'll use little b or capital B for baryons. Please bear with me. The way that this is defined, this is the number density of baryons minus the number density of antibaryons over the temperature cube. This gives us a sense of how many baryons, or the imbalance between baryons and antibaryons, as compared to the number of CMB photons, like proportional to the temperature cube. And experimentally, we see that this number is some 10 to the minus 10. So there's 1 baryon per 10,000 million photons. And in particular, this contribution in here is tiny. We find that there's this imbalance, tells us that there's many more baryons and antibaryons, something that is perhaps very familiar to people here in the Institute. We don't find much antimatter when we look around. We don't find anti-galaxies. But it's somewhat very surprising to a particle physicist, and in particular, it's a huge number for us. Why is it a huge number? Well, this is because production of this asymmetry is a complicated process that requires a number of conditions. These were outlined by Sakharov in '67. Let's go quickly through them. They're somewhat intuitive, really. One of them is charge parity conjugation violation. Charge and parity conjugation is just taking a particle to its antiparticle and flipping the sign of space from x to minus x. This should be broken for this asymmetry to be generated. It should also occur, this process of the generation, out of equilibrium. Otherwise, equilibrium tends to balance out any imbalance. And also, as it is perhaps intuitive, baryon number itself, or baryon symmetry, should be violated. And just a reminder, or to be specific, what I mean by baryon number or baryon symmetry, as we'll actually review explicitly later on, from any symmetry in our system follows conserved charge. Baryon number in all lab-based experiments we've seen to be a conserved quantity. In particular, we define the charge, the baryon number charge of a quark to be 1/3. And as you know, a proton is made out of 3 quarks, so it has a baryon number of 1. and an antiquark has a baryon number of -1/3, so an antiproton has a number of -1. And again, this is a piece of evidence for physics beyond what we know in particle physics, the standard model, because what I said, in the sense that this is a huge number for us, is coming from the place of knowing that in the standard model, with the physics we know of, this number should be basically 0. So that's another piece of fundamental physics input that we get from looking out into space. So let me now go into propose solutions to these questions, in particular to dark matter and baryon asymmetry. I won't go into the details of any model in particular, but rather I'll try and focus on general mechanism and ideas to make things work. So let's start with dark matter. First of all, how does it get to be out there in the first place? How do we produce it? And that will be the topic of these few slides. One possibility is thermal production, which is to say it was producing this primordial plasma that was in equilibrium in the very early universe. This, in a sense, at least the first idea, which is the freeze out, is based on a successful mechanism, or something that we've seen at work already out there in nature. We've seen it in the successful predictions of Big Bang nucleosynthesis and also the CMB decoupling. So let me sketch it quickly here. So imagine this is basically time, this scale here, and this is the number abundance or the yield. Very early on, we had that if this dark matter particle had sizable couplings to ordinary matter, it could be produced in the primordial plasma, perhaps with the collision of two photons or baryon-antibaryon. And if this process is frequent enough, you will reach equilibrium. You will reach a state in which the production of the particle and the annihilation of the particle back into standard model particles reaches a balance, and you have basically a thermal abundance of this particle. Now, when the time goes by and temperature decreases, at some point you'll hit a temperature that equals the mass of the particle. When you do this two-way process gets shut down in one direction, which is to say, on average, particles don't have enough energy to produce this dark matter particle. But you can annihilate two of these dark matter particles back into bath or standard model particles. That means that its abundance starts decreasing fast as it only annihilates, but it's not being produced. And it would actually dip down to 0 if it follows its equilibrium abundance. But the expansion of the universe comes to the rescue eventually, because if you have that this particle is more and more diluted, it's harder for it to find each other and annihilate, and you're left with a remnant abundance of this particle. And also note that in this sense, if we increase the cross-section, or if we rank up the interactions, it will annihilate more and will end up with smaller and smaller abundances. You might have seen this plot in other places. And this is the mechanism, but the prominent candidate in this regime is what is called the weakly interacting massive particle. It's a particle produced with this mechanism that interacts through the weak interactions that rather miraculously come out to be of the right order of magnitude to produce the observed relic abundance. A twist on this production mechanism is the freezing mechanism. The dynamics, the basic equations that govern the dynamics are the same, only in this case, the particle is not as strongly coupled. So you start producing it, but you never quite reach equilibrium. You never have that the inverse process equilibrates the system. So you slowly build up the abundance of this particle. And when you cross the threshold of its mass, you can no longer produce it. And you're stuck with however much you produce at that stage. In that sense, the dependence with couplings is the inverse in here, because if you increase the interactions, you produce a bit more and more of it. But either way, for both of these cases, there's a lower bound on the mass of the particles that can be produced. In particular, for freeze-out, you cannot mess with the big bang nucleosynthesis. So the masses have to be larger than the mega electron volt scale. For the freezing, you can push it a little further down, but not much further down. But let's try and think of going beyond this bound, perhaps with a different production mechanism. A very general feature of pushing the mass down, it doesn't depend on how it was produced, it's just if you can picture this process of lowering the mass of the dark matter, is that, well, first, as we push it further and further down, it gets crowded, which is to say, occupation numbers are larger than 1. Let me expand a bit on that. What we do know about dark matter is its energy density. But then its number density is given by its energy density over its mass. And this is observed experimentally. So if we push this further down, we'll increase the number density. There will be more and more dark matter particles per unit volume. And at some point, we'll hit large occupation numbers. And to remind you how these occupation numbers were estimated, if you put the wave function of a particle in a box, you'll have that you can feed a constant or a wave into the box, or 2 waves, and you can compute them up the number density of states per phase space, or per momenta, or wave vector. And this is simply given by Planck constant to the cube. Now, if you study a particular system where you know something about the momenta or the wave vector of dark matter, say if you're looking at a galaxy and you know via the virial theorem what's the typical momenta of dark matter. Then comparing these 2 magnitudes, this one times the typical momenta of the system, you can see when this density overtakes this other state density. When that happens, you'll have more than 1 particle in a given state. And that would mean large occupation number will get larger than 1. And you actually enter the field regime, in which you rather describe your substance as a field rather than separate particles. Now, of course, this is for bosons, but if you have fermions, you cannot put more than 1 particle in the same state. And this actually presents an unsurmountable bound on the mass of dark matter. You cannot have that dark matter is smaller, its mass is smaller than the kilo-electron volt scale because of this type of bound. You just cannot compress it enough. At some point, you'll have to put it in ever higher momentum state that will be larger than the escape velocity, and it wouldn't be a successful dark matter candidate. But let's stick to bosonic matter in that case, and push further down the mass even. If we push it further and further down, we hit the fuzzy regime. And this, surprising as it might sound, is a regime in which we hit quantum mechanics at a galactic scale. In particular, the Broglie wavelength of the particle is given by the inverse of the momenta as proportional to the mass. So if you keep decreasing the mass, you'll hit the Broglie wavelengths larger and larger. And in particular, as we know from quantum mechanics and the uncertainty principle, we cannot localize a wave function in a space smaller than the de Broglie wavelength. But we do know that dwarf galaxies, which are the smallest objects dominated by dark matter, have a given size. So if we want to localize dark matter within the smallest objects we think dominated by dark matter, we cannot have an arbitrarily small mass. In particular, it sets a limit of 10 to the minus 22 electron volts. And this hits the fuzzy regime, something that actually Diego Vlad will talk about on Thursday, so I won't say much more about it. But this is the absolute limit, if you want, for the mass of dark matter. Now, how can we produce such a candidate? It cannot be produced thermally, so it should be athermal. It can have potentially a very small mass, and it also should be weakly coupled enough that it's not produced by the previous mechanisms. This can be done, and it is the case example for axioms, if you're familiar with that. But basically, the way to produce it is we put this field that will describe, like we said, we enter the regime in which this substance behaves like a field rather than a particle, a field that we'll call phi, and we can study its evolution, just as we will study, say, the dynamics of the electromagnetic field, by putting into our Friedman-Robertson-Walker metric, that metric that we wrote later on, and the dynamics of the field with a mass m is given by this equation of motion that contains a friction term, that's Hubble there, h, times the first time derivative of the field, and then the mass term. The evolution of these fields looks as follows. At very early times in this regime, the Hubble rate dominated. This was like a friction term that holds the field still at a given value. Once we hit the time at which the Hubble rate equals the mass of this particle, the mass term starts to dominate and the whole thing starts to oscillate with decreasing amplitude. Now, the fact that this can be a successful dark matter candidate can be realized when you plug this solution into the energy momentum tensor for this particle and see that it's dominated by basically the 0,0 component of the stress energy momentum tensor. So it behaves like a cold substance. There's of course a question of what set this initial value of the field, because you have to choose it right to get the right dark matter relic abundance that we know today. And this is actually something that it can be given by inflation, but that's in some sense unsatisfactory because it just tells you it could be anything. Let's just make it what it has to be the right relic abundance. But that's actually something that we'll discuss given there's time a little further on. Let's turn now to baryogenesis and ideas to solve this type of problem. I will first talk about heavy particle decay. That is the case, in case you've heard these buzzwords before, grand unified baryogenesis or leptogenesis. And I guess this is based on the primordial plasma. And it goes as follows. Originally, again, at early times, there was a thermal abundance of a new heavy particle. In the case of grand unified baryogenesis, there could be the extra scalars or extra gauge bosons of those models. In the case of leptogenesis, will be a heavy right-handed neutrino. And again, after we let time evolve and cross the threshold of temperature equal to the mass of this heavy particle, its abundance will start decreasing, but again, it will leave equilibrium at some point. So we've already have one of the check marks for Sakharov. It has left equilibrium. Now, as opposed to dark matter, this particle is not stable. We typically assume that dark matter is stable and it doesn't decay because it hung around to be here today, 14,000 million years later. But these particles are not stable, so they will start decaying again, as opposed to a relic abundance. And then the two other ingredients enter this mechanism, and that's CP and baryon number violation, in the fact that the decay of this heavy particle X to some other particle with baryon number B is not the same rate as the decay of the antiparticle to an antibaryon. And this generates an imbalance of baryons over antibaryons. And it's a pretty well studied mechanism. Is not so. The case of grand unified baryogenesis is not so well reconciled with experimental data these days, but certainly leptogenesis is a viable possibility. And just to be comprehensive, I mentioned another way of producing this asymmetry, which was thought to maybe work for the standard model before we discovered the Higgs, but now we know it's not the case. And this is baryon asymmetry generation in a strong phase transition. By strong phase transition, I mean a phase transition in which at some epoch in our universe, we're trapped in a local minima where the true minima in our potential is somewhere else. If the barrier is high enough, this will mean that bubbles of the true minima will spontaneously create and expand to cover all of space. On the edge of these bubbles, we have non-equilibrium conditions, and if our fundamental symmetry against violates CP and baryon symmetry, in there we could produce enough asymmetry. Again, this doesn't quite work in the standard model, but people have added new potentials for new particles to make it work, and it's a viable paradigm these days. Okay, so that's, sorry, I'm rushing a bit through this, but again, any question about it, please let me know. Because now I'm going to talk about my grain of sand in this beach and the possible connection between baryon asymmetry and dark matter. Unavoidably, I'll have to talk a bit about theoretical tools that we use in particle physics, but I'll be rather simple and sketchy in what we need to actually understand what's going on here. So first, we start our theory description of a system, specifying our particle content, and that is first given by the fields in our theory. So for example, picture the electromagnetic field. We know that it's given by a vector potential and a zeros component that we can feed into four component Lorentz vector. And as you also know, associated to this electromagnetic field, there's a quanta, a particle, which is the photon. In the same sense, for any field we'll introduce in our theories, there will be an associated particle with it. Now, the dynamics of the electromagnetic field can be described by an action principle. That is, in this case, given by the field strength square and the possible coupling of the photon to an electromagnetic field to a current. Euler-Lagrange equation will give us a Maxwell equation in this case, and this will give a classical field evolution, if you wish. When we look at the quantum version of this theory, this action will give us the interactions of the theory and how, for example, an electron comes together with a photon to be scattered in quantum scattering. That's pretty much what we need to know about this our description of physics. And now I'm going to review another topic of physics, which you might have forgotten about, but I'm sure you heard about it early on in your physics undergraduate, and that's Nether theorem, which is particularly useful in particle physics and for us today. So let's introduce a field. Let me just quickly review it. A field, capital phi, and its Hermitian conjugate, also phi bar, and assume that there's a potential that depends only on the contraction of phi and its Hermitian conjugate. It will look something like this, for example. Now, this system has a symmetry in the sense that this potential doesn't depend on the phase of this field phi. How we say that explicitly in terms of asymmetry is to say that the field phi rotated by a small amount epsilon, just phase times this field phi, that we can expand if epsilon is small enough. And we know that the variation of the Lagrangian with respect to this deformation with this parameter is 0 because that's a symmetry of the system. If we further make this parameter space-time dependent, in this variation we pick an extra term that depends on the time derivative of this parameter times another coefficient, which we define to be the current associated with that transformation. And the right-hand side we can rewrite as the equation of motion, basically, so that is 0. So what this is telling us, after we use integration by parts and take that derivative over to the other side, is that the divergence of this current, the contracted time derivative times the gradient, equals 0. Explicitly, for a given system, the zeroth component of this current will be the sum of the particle abundance of a given charge. So there's a sum in here. In our case at hand, we know that the field phi will produce a particle, but there will be an associated antiparticle with the field phi emission conjugate. For example, we have in this sum, we have 3 particles in a given volume and 1 antiparticle. This will be 3 minus 1. And the space component is proportional to the velocity of this fluid. And as you know from differential calculus, we can integrate over space. The first component will be the charge integrated over that volume we're considering, and the second component will give us that the change in that charge equals the amount of substance that is living through the boundary of that volume. Or if you take this surface to encompass your whole system, or take it to plus infinity, this is 0, nothing escaping, and this is giving us the conservation of that charge, as I'm sure you by now have recalled. Well, now let's use this piece of physics that we know of and recycle it to look into the fields of this theory. Now, there's a certain degeneracy in here when we say that we can do a phase transformation with the parameter epsilon that depends on space-time. If we decompose our field into a modulus, we want in these coordinates the radius in here, and a phase that is little phi over f for normalization. So this transformation looks like a shift in this phase variable phi. Or we could actually swallow it up and reuse the results that we had on neither theorem to look into the properties of this field phi. The first one that we can recycle from the vanishing of this partial derivative of the Lagrangian with respect to the field. We know that this vanishes, which is to say we know that there's no potential associated with this direction. And that's visually intuitive because we're saying that is the phase of this field and the potential doesn't depend on that phase. In particular, this means that there's at this order no mass for this particle. So naturally we can get a light mass for this particle in here, and it's justified by symmetry. And this other term tells us about the coupling of this particle to an external sector, and in particular, its coupling is proportional to the divergence of that current that we just saw. And that means that if the symmetry is exact and this divergence is always conserved, this term is 0 and the particle doesn't couple. So this also gives us a small coupling naturally. But let me move ahead and speed up because I don't want to take much more of your time. Our basic idea is to put together what we've been talking about and say that this symmetry, how about making it a baryon number that we've been discussing about it for some time now. And at the same time making this field phi, this Goldstone boson, that's what that is, be a candidate for dark matter. Well, for this to work, this symmetry should be broken so that it couples and it has a mass. But we happen to know that there's evidence of this symmetry being broken. We just review that in our universe as an imbalance over baryons over antibaryons. Let me just sketch how this works. This very same baryon current was in the very early universe. It had a mean value of 0. There was no imbalance. And then whatever process occurred at some temperature, time, whether it was leptogenesis, electroweak phase transition, we ended up in a situation in which an imbalance was produced. And in between the two, the divergence of this current had to be non-zero. So it was indeed a breaking of this symmetry cosmologically. We go back to the equation of motion for that field. This imbalance in the symmetry here, this is a rewriting of that divergence in Friedman-Robertson-Worken metric. Fed like a source term in the equation of motion for the field. Remember, this part was there before for axion or Goldstone boson candidate. Now, for a candidate in particular, there will be a source term on top of that. Now, if this occurs at some original time t, in particular, much smaller than the inverse of the mass, so again, it's dominated by friction, we'll have that there's like a transitory force that acts quickly on our system. which is to say something like a kick on this field that push it higher up, and then friction again will stop it. And then after a time, it will start oscillating again. So visually, this is what we have in this case. And we can compare with the previous case without a source, the case of typical axions, in the sense that we're generating these initial conditions with our kick. So we're sort of addressing that possibility. It's not given by inflation, but it's actually given by matter-antimatter asymmetry. Then we do the math and compute the dependence of the abundance of this field on the mechanism of generation. It will depend on the mass of the particle, the temperature at which this asymmetry was produced, and a factor which is order 1 if you couple this to baryon number. We were a bit more general in the paper, but never mind that now. We find out trivially that there's a parameter space for which the whole thing works with all of the constraints that I don't have time to go through. And those are for masses around the 0.1 gigaelectron volt and a coupling constant, which is this F, that's 10 to the 12 gigaelectron volts. And just a very quick word on what this feels like. We saw that the actual dynamics of this field were rather simple and we could understand with classical mechanics. There was a very quick force applied on the system, and then it was left to evolve with this friction and mass term. So in a sense, it's like a flash in the early universe. This was this sudden switching on of our source and switching off, and the remnant radiation that this quote unquote radiation, the production of this field that this produced has lingered on to be the dark matter today. And then we can put this actually together with the previous mechanism and find that there's an analogy between this freeze-out mechanism in which we start, it's just visually for now. For freeze-out, we start with some constant abundance that then decreases and gives us a final relic abundance. Freezing, we start from 0 and then it's increased by the coupling. And the analogy there is that in our kick alignment mechanism, that's what we call it, as opposed to misalignment, we start with a small abundance that it builds up as opposed to already given original initial condition for the field. So let me apologize for running over time and finish it here.
Thank you, Rodrigo. Thanks a lot. Okay, so now it's time for questions. So please raise your hand, use your device, use the reactions label in the Zoom window in the bottom. And if you want to ask a question, just I can unmute you, or you can even type your question in the chat. So there's one question here by, let me see, find who he is. Yeah. Oh, Rafael Rebolo. Okay. So Rafa, just give me a second, and I'll get you. Let me try to. Yeah. Now you should be able to unmute, Rafa. Can you unmute? Can you talk? Otherwise, I can do it. No, not yet. I cannot hear you. Wait. Just a second. Yeah, for some reason, let's see. Yeah, you should be able to unmute now, Rafa. Can you not? Oh, yeah, you can. Yeah, there we go.
Thank you. First, thank you for the talk. My question is rather simple. Is this ultralight particle affecting the expansion of the universe at the time of nucleosynthesis? Would it have any effect on the primordial nucleosynthesis?
No, to leading order. No, there's some dependence on where and what is the mechanism for baryon asymmetry generation. In here, we assume that it was leptogenesis and that it occurred very early on. We're talking about temperatures of 10 to the 12 gigaelectron volts, maybe. Then dark matter was produced via this mechanism, and we assume, there's something to be checked, but we assume that its contribution to the expansion was negligible by the time of Big Bang nucleosynthesis. It only later took over as dark matter. But that's, of course, something to check. This plot is basically checking the consistency, and we looked at these type of questions for that.
Okay, more questions?
Well, there's a question from John on the chat, I can see.
Oh, yeah. This question is, what could be observed to test this idea?
That's a great question. That's always a good question. So in this case in particular, we couple to not only baryon but lepton number, because we were allowed, this is to make it successful, basically. And in particular, that means we're assuming Majorana neutrinos and lepton number violation, and that means that this particle that has giga-electron volt mass could decay into neutrino-neutrino. Actually, there will be Majorana in that case. So the coupling should be small enough so that this hasn't happened in the age of the universe, basically. So its lifetime is really, really long, which is to say it has a very, very small coupling. This we can do naturally, as we discussed before with this type of model, but it does set a non-trivial constraint or a system. That's basically below this blue line, we don't have a successful dark matter candidate because it decayed too early. But potentially this could be the signal. Maybe if we see this type of dark matter, if we're lucky enough to see it decay inside Kamiokande, for example, into a couple of neutrinos, and we can detect that signal, that would be a way to tell that this is a successful model for dark matter.
I see. Okay. All right. More questions for Rodrigo? I see one hand, but this is Rafael's hand. Yeah. Anyone writing any question on the chat?
I encourage students to ask questions, and there's no silly questions to ask. It's only me explaining it poorly.
Yeah, well, you are shy, it seems. Yeah, no more questions. Apparently. Jorge, do you want to wrap up? No, there's a question in YouTube. Thank you. Thank you. I hadn't checked this. Actually, let me see it. Here it is. Yeah. Nuno Morocco is asking, it's possible, hi there, it's possible matter, antimatter, and microscopic black holes are created little after the Big Bang. And microscopic black holes absorb the antimatter and disappear. Let me reread this again. So is it possible that matter and antimatter and microscopic black holes are created just after the Big Bang, and then microscopic black holes absorb antimatter and disappear?
Not sure I fully comprehend the question, but there's that somewhat. Orthogonal to this talk, there's a possibility that dark matter, well, not all of the dark matter could be black holes. There's a possibility that some of it is black hole. The production of these black holes in the early universe requires new physics as well, and dynamics. And then with perhaps mixing this up with the fact that the argument that black holes violate baryon number is often thrown around. I see. So maybe that was a question about, yeah. So you can throw baryon charge into a black hole and wait till it evaporates, and that will generate an imbalance. However, in my understanding, this process is not frequent enough in the early universe to actually produce the dark matter, the baryon abundance that we see today. But I'm not an expert on the topic.
All right. I've checked the email from the seminar account. Apparently there are no questions in the seminar email address. So, okay, one more chance for questions for Rodrigo. So this is, well, just a short question. This is related to what Rafa was asking. This is, nucleosynthesis happened well before the CMB, and there's no hope to see this as the energy release gets thermalized well before the coupling, right? Well before the recombination takes place. Any energy released to the in this process would quickly be thermalized, right? Because I guess you're still dominated by the huge entropy of photons. So, I mean, what redshift roughly would it happen?
So let me see. The thing to check out, the one relevant parameter in this type of mechanism is looking at this Hubble rate versus the mass of our axion or light dark matter candidate, because it is starting at this time when it behaves as cold dark matter. So that, well, certainly you should have that it behaves as cold dark matter early enough before structure formation, and actually even earlier than that, and that this has no sizable contribution to the scale, to the Hubble rate at the time of Big Bang nucleosynthesis. So basically, yeah, this should be, the contribution from this mechanism to the total energy density should be negligible up until after Big Bang nucleosynthesis.
Okay. So kind of access this via CMB observations. All right. So if there are no more questions, let me check again the YouTube channel in case there's any other question. Thanks. He was just thanking you, Nuno Marocco. And also John Beckman is thanking you for a clear presentation. So I think that's it. Thank you, Rodrigo, for this very nice talk. Yeah, and it was great having you around, and it's great having you around, and you'll be here until the 20th, I've heard, if I recall correctly, right? So, okay, so I think we can close here. Thanks a lot. Bye-bye to everyone.
Thanks for having me. Thank you.